Hello, sir. Good morning.
How are you? Good morning. Okay. I don't know if anyone else will be here today, but we'll see.
Yeah.
Any updates on your end, or?
Yes, sir. I've been trying to understand, we have discussed in the last time that, how do we, save the representations? I mean, the input features and, the input structure. So next, I've been trying to understand, the message, I've read the message passing mechanisms and, the way that we wanted to train the neural network. So that part, the hypergraphs. And I was thinking in the direction that, to understand, holistically from starting to designing input feature, then structure, then message passing, and to fix the pipeline so that, we can start thinking about it, which component should be, at each stage, so that it will become like a, good way of learning the, embryogenesis of C. elegans. How can we order the higher order interactions? How can we, how can we, model the higher order interactions? What could be the best possible way? And yes, I would like to discuss about the paper little in detail.
Good morning.
Hi, how are you?
Sorry.
Managing to rewrite my thesis, and I'm trying for about 7 pages.
Oh, okay, for a paper.
Yeah, I think I can do it.
Oh, good, yeah.
Anyway, that's all I'm doing.
Oh, wow, yeah, good luck, yeah.
I can start it right now, sir. So first, I will start from the paper itself, because this is what I have for our purpose, like I mentioned, pros and cons. But before that, I wanted to go deep into the paper itself.
Okay.
So to give a quick recap, so last week we discussed about the encoding, the input feature and the input structure. So here we understood what kind of input feature that we can give it to hypergraphs. One is like external information, like providing the information that it does not have, and the structural information, which directly accounts the information that is from the graph itself, and design it encodes certain extracts the properties of the structural features, and it encodes into the input feature itself, and identity information. So treating each and every representation as a unique value, and assigning hypernodes in such a way that assigning hyperedges in such a way that the set of hypernodes come together to form a higher order interaction. That's one way. These are the 3 different ways of doing input features. And input structure, we have seen reductive transformation, the transformations which we do, and after doing so, we cannot bring the graph back. So that is like clique and adaptive expansions. And non-reductive is something that we have a hypergraph structure. We can transform into certain transform into certain way, and we can bring it back. So like star, line, and tensor expansions. So these we discussed last week. And this week we're going to understand about the message passing mechanisms and the objective that is related to that. And, we can jump into the message passing. So here last time, sorry, sir, if you have any questions, you can just interrupt me in meanwhile itself, because...
Yeah,
okay. So anyone can interrupt in the meanwhile if they have any questions. So here is the graph. So suppose G is the graph and V are the hypernodes, and E is the hyperedge. So the H is the incidence matrix, and the X are the node features, and Y are the hyperedge features, the edge that carries. So P is the embedding nodes of the Lth layer. So when we design a graph neural network, so we believe that it has like L number of layers. So we call it Lth layer, which is denoted like this. And the hyperedges are designed by like Q. And So here we can see that the shape of the P-th layer is like, the cardinality of V times the K. So here K is something we design because each layer has different dimension. So that's K is the how many number of dimensions it has. The incident hyperedges is given by n subscript the hypernode, and IN is n by n identity matrix. So I is indicator function, sigma is like nonlinear activation function, and M is basically a matrix. I determines the row and J determines the column, or I comma J determines a single entry in a matrix. Okay, so let's go into like the part that we were discussing, like left off last week. So yeah, so message passing. So how do we pass the messages in order to have that makes the higher order interaction more effective? So they use this. Some people call it as message passing mechanism. Some people call it as aggregation function. Some people call it as neural message passing functions. So it's like it's just a jargon that varies here and around, but the concept is just the same. How are we trying to encode these representations, and how are we identifying which node carries the correct information so that we make a right prediction? So while doing this message passing, message passing aggregations schemes in the higher order interactions, we have the three questions. They compute these three questions. The first is whose messages should be aggregated. So whose in the sense which set of nodes or which set of hyperedges. So what messages should be aggregated and how should be they aggregated? So these are the three different line of questions that we're gonna see. So first we'll start with that whose message should be aggregated. That is target selection. So target in the sense which set of nodes, so that we aggregate this set of messages. So for the message passing, so we generally should decide like which message to aggregate based on the structural expression of the hypergraph that we have, and provided the representation examples. Suppose we take an example of like one clique expansion. So where we do a clique expansion, this clique expansion, again forms a interaction that is similar to that of dyadic nodes that we generally see. So it's very similar to that of simple graph neural networks, and the one clique expansion based on hypergraph neural networks was seen by a few set of. So we often see there are like certain interaction techniques that we see. So similar to that of hypergraph spectral expansion. Here we have a new type of hypergraph spectral expansion, where they call it as simplifying hypergraph neural networks. This is one of the good paper that was published in ICML, I believe it's in recent 2024 paper, where they have simplified how can we use a one-click expansion to that of hypergraphs, so that we can use it similar to that of once we do this one-click expansion, it becomes like a dyadic single order interactions. There is no higher order interaction. There's a dyadic interaction. So on top of this dyadic interaction, how can we induce these hypergraph properties using that is what they have tried off. And I would make some like points like what are the pros and cons of this approach. So in target selection, this the approach that the information passed between nodes are connected by hyperedge and focus on the interaction between the pairs of nodes. So the main disadvantage that we see is, again, we get a dyadic interaction, and the higher order interactions or the indirect interactions are not captured. And these may have become little computationally expensive because it does not consider full structure of the hyperedges. So that's the main two differences, and one-click expansion and all. Next, we see one-star expanded graphs. So where we try to expand from the given, you have this hypergraph-based star expansion. This message pack can occur from a set of node groups to that of like hyperedge group. And we can do the same, like hyperedge group to the node group. So, and for that, what they do is, so at the first layer, so we know that P stands for like hypernodes and Q stands for hyperedges. So the nth layer of each node carries information of the previous layer and aggregates using a nonlinear neural network. Here we can say it as an MLP, or we can take another, small transformer block, but it's the way of representing. So they use a nonlinear transformation to transform this set of features into certain space. And there what they perform is they try to find out the, the message passing between these two set of layers. And later they encode this information into another MLP. So this is more like, designing, three different set of interactions and bringing all them together. Like, we use different MLPs so that, to form these higher order interactions, believing that, these edges randomly captures these set of nodes, the features that they have observed. And then, so subsequently in equation 5 that we see that this transformation, and in equation 6 we see that the node embeddings are updated by aggregating transformed embeddings of the incidence hyperedge. So here this is our incidence hyperedge, and this is our previous node hyper edge features, and based on that they aggregate into this, and this uses another nonlinear transformation in order to aggregate the full-fledged the hypernode level features. So I think this was morely extracted from the paper like the simplifying graph neural networks. So this is a paper which goes more into details of how this was performed, how they use this MLP block in order to acquire the higher order interactions. They have detailed everything, very clearly in this, and they have like lots of experiments which are not, they do not belongs to the, C. elegans, but they really are a little bit of close relation, so that, we can think of like, how this has been done. So this is one line of work they have. So they use standard set of data sets, and they have shown that this method is kind of effective. So that's one way. So this is one way of representing the, sorry. So you have any questions?
Not right now, no.
Okay. So yeah. So this is a target selection. So this, which set of nodes that we want to aggregate, the messages. So is the first. Next. So what kind of messages that we passed or in order to aggregate as to given. So the message itself, we call it as a representation or a message representation. So after choosing the targets, once we choose, okay, these are set of the hypernodes or hyperedges that we wanted to, focus on. In our case, we can see it as like, the hyperedge forming the synthetic tissues, believing that, okay, these all form, these are all the networks, or these are cells that we form the synthetic tissues. So believing that, we can say that, okay, these are our target, selected target for, we have 5 selected targets, 5 synthetic tissues, and say that, what kind of message that is to be given to them in order to, make our process complete. So what are the messages that we aggregate is, after choosing the message target, the next step is we determine the representation. So what kind of representations are like in hypergraph neural network, we use embeddings of the previous layers as a message. So generally at each and every layer, so once the interaction happens, and then it pushes to another layer, and the layer 1 and the layer 2. So suppose we have like 3 layers. So each extracts a certain set of nuances, so that the graph or the hypergraph will be able to get all the necessary information at the right particular node. So at each layer we have extracted decent level of representations. So when we say like we have 5 synthetic tissues, and we have a hypergraph of like five hyperedges and some set of nodes, and they have their own connections using this hyperedge. So when we say that, the message representation, then here what we mean is, so when typically once we give this to a hypergraph neural network, then it tries to understand that maybe the first three are it will try to understand the connection between the central tissues of 3 central tissues in the first layer, maybe 5 in the next layer, and it tries to aggregate the information in the third layer. It's not exactly how it's done, but in a similar fashion, each and every layer has its own layer representation, but it tries to understand, tries to acquire the features that are relevant to that of the hypergraph that we build. So this is like one of the important steps that we use. So we have hyperedge consistent messages. So this is like a standard approach, like most of the significant papers use that. So they call it as a unified representations, because each and when there is a hyperedge connection between all the set of nodes or the hypernodes, then we believe that it has to share the information equally, distributing to all of them. And that's the main concept of this hyperedge consistent messages. So how it's done is, simply it aggregates the information from each of the layer, and then it uses a small epsilon as a simple learnable parameter, and it tweaks upon that by using a simple nonlinear function. So theta is basically a trainable parameter, and this is a aggregation of like the hyperedges and the hypernodes at the previous layer that's encoded. And that is done with a uniform way. So all the hyperedges gets the same information. So all the hypernodes get the same information from the hyperedges. So, and hyperedge dependent messages. So each and edge carries a different layer of information, and this is passed using it's not exactly given to each and every node in a fixed or uniform fashion. So they use an MLP in exactly we see here. They use an MLP. So the main use of MLP here is they transform, suppose we have 10 number of, hyperedges, one hyperedge and like 10 number of hypernodes, and it's uniformly distributed in the previous case. But in this case, it distributes based upon certain weighting mechanism. While training the hypergraph neural network, we will be able to, tune these weights and get the weights appropriate to the problem that we are trying to solve. So this is one way of trying to do it. So this is hyperedge dependent messages. And there are certain works where they have used that, this what's next is one of the paper which introduces within order positional encoding to adapt to the certain node messages for each target. So suppose we say that, there are only certain set of central tissues important inside a hyperedge. Then we give a little importance to them instead of giving a uniform way of, giving importance, so that, it makes a stronger connection while doing so. So this is one of the way to do it. And here the F represents a node centrality matrix, and T and FT represents the number of centrality measures that we use, and T centrality measure score of like node VI. The order of the element C is set of capital C, and they are trying to explain this exact paper what they have done in the what's next. So, and it's the order of C, and that's how they are able to calculate this VOP within order positional encoding. And using that, they'll be able to map it to the each and every node and hypernode, so that the hyperedge has its the weighting mechanism, and it becomes like a hyperedge dependent messages. So next, once we have got given the features exactly to the hypernodes and the hyperedges, and we distributed it in a certain fashion, now how do we aggregate these? When we are you do a task called based on the given network, can you determine whether this this whole hypergraph system of C. elegans will be able to survive or not. Suppose we take that case, then we use aggregation functions so that the information is totally aggregated, and then we get to a desired label, and we classify or we do some sort of things. Or either we can do how much weightage that each and every the message or the node, the hyperedge should carry, depends on the aggregation function that we use. So there are several functions that previously people have done. In the standard graph neural network, we see summation, we see multiplication, we see pooling, we see simple MLP also an aggregator, or we use transformer layers as an aggregator. There are several other mechanisms that we use in graph neural network. What we try to do in this hypergraphs is we use a fixed pooling mechanism. So fixed pooling is basically this includes the summation, the average, and these are the certain which I have mentioned previously. These are fixed propagations. Instead of adapting to certain hyperedges, we used a fixed. Believing that this node should be aggregated using the sum function. So the hyperedge, whatever the nodes carry the information, all the hyperedge, we do a simple summation or simple multiplication. So that's one way of doing. And so in learnable pooling, what we use is, so there are several other mechanisms, several hypergraphs. They use pooling functions and attention mechanisms and do a weighting strategy for the aggregation. So these are more of target agnostic attention. So what we mean by target agnostic is, so as we design certain set of targets here in this space, right? Believing that, this has to, only we are focusing on these specific set of hyperedges or these specific set of hypernodes. For that, what we try to do is we apply this attention so that only the targets gets more, the significant weighted proportion. And this target aware attention gives more weight or more, significance to that of the, the hyperedges or the hypernodes that we wanted to do. So all say transformer, and so this is multi-head attention that they have used for in that case. So here, suppose the S is basically the, the embedding of the incident hyperedge. For that embedding, what they're trying to do is first apply an MLP and then use a weighting function, which can be, probably a learnable parameter. And we apply on top of that an MLP with that, and we try to understand the attention. So here we see this more looks like an, this MLP of S will give us n-dimensional feature, and MLP of S gives the same n-dimensional features. So the difference here is, here we use for t, 1, which means that, for the previous time step, and here t, 2 is basically the next time step. So that's how we try to embed the information. And when we multiply these two, then we should be able to get a good, dot product, or the, similarity between how this, attention got imparted into the layers that we want. So once we are doing this attention, so if we apply it more, then the value gets the values that are lesser important will come close to 0, and that are more important will go close to the value that we desire, or that is 1. So that's how we give certain weighting mechanisms. Here the layer normalization and other are basically to balance out certain things called a gradient explosion, or a gradient explosion, or something what exactly it is. So the weights all become 0, and that's one of the case. So yeah. So these are the certain ways of doing it. This is a multi-head attention, and this is one of the good paper where they have applied hypergraph neural networks this is one way where they have done. They apply attention at each and every layer, at each and every embedding node. So here we can see that attention is applied at the hypernode and hyperedges of the previous layer, and then they encode using a theta, which is a parameter. So it's like a learnable. So these are the and this is again aggregated using a sigmoid function. So this is more like a these functions act more like a global type attention, and these act like a local type attention. So these are applied inside the hyperedges that we want, and this is again globally aggregated from all the hyperedges that we have, and the hypernodes that are inside that hyperedges. So this is more. If we have little more time, then we can go into details of that paper. But as of now, let's get to the overall structure. So this is what like more of message passing mechanism. So what are the targets that we select? The first thing, what kind of messages that we want to pass is the second, and the third is what kind of the third is what kind of aggregation function that we are trying to use in order to get the desired representations. So these are the three different stages of applying message passing mechanisms to the hypergraphs. So once this message is passed, what we want to do is we wanted to learn to do certain tasks. So these are like let's go little to the taxonomy to see a little change. Yeah. So we have seen that we have seen node to node, node to hyperedge. These are the different message passing mechanisms that we can see. And this message passing, once the message is passed, we have to learn to aggregate the correct messages into the right set of hyperedges and right set of hypernodes. So for that, we need a objective function or the loss function that is very much aligned to the problem that we are trying to solve. So that is the last step, which is like the objective function here. So here in the objective function, so there are like, generally we try to do this paper mostly focuses on these three tasks. One is learning to classify. Classifying these set of nodes as, saying we build a hypergraph and we say that, okay, these set of nodes actually corresponds to, these set of nodes actually corresponds to centential cells. In order to do that, what is the correct objective function? So we have learned that message passing mechanisms and how do we design, what kind of information that we give into that is all we have known. So how do we classify them? Saying that, these set of, cells are, form like an higher order interaction and form a centential tissues, or say that, these form like, motor neurons, these form more like a, sensory neuron, and these form like a, like a different set of neuronal groups that we actually see. So how can we, formulate and, learn to classify, learning to contrast, or learning to generate these set of things. So these are like, the objective function is one of the fundamentally important thing that we do to get our hypergraph neural network to, learn. So hypergraph neural network can learn higher order interactions by classifying hyperedges either positive or negative, saying that these are the set of yes or no binary type interaction. So a positive hyperedge is a ground truth or a true hyperedge, and the negative hyperedge is generally a heuristic or a generated hyperedge, or we say it's false. So you have predicted wrong. Suppose that's a fake hyperedge. So this is a table that I'll discuss later, because this is more of it's more of all the things aggregated in the same place, saying that what we have done till now and what are the papers that were published and what are the years of them. So I will discuss about this once I'm completed with the objective. So the heuristic negative sampling, they call it. So what they say is they have a negative hyperedge containing k random nodes, and they believe that they form small motifs. So each negative hyperedge contains a randomly chosen k adjacent nodes. So these are negatively sampled motifs. And we also have negatively sampled cliques, which are like each negative hyperedge is generated by replacing a randomly chosen node in a positive hyperedge with another randomly chosen node that is adjacent to remaining nodes. So it is like negative. How this negative sampling works is, so we have say that these do not come close together, or these do not have any similarity, then we call it as like a negative. So that in this negative, what we are trying to do is, so first we determine the size, and we determine the number of motifs and the number of cliques. So once we determine that, then probably we can do that probable negative sampling. So based on that rule. So how can we do that? So how can we learn this negative sampling? So there are like several objective functions that can be applied at we can say that in order to classify, we can use a simple saying that this is this color, and not color exactly, this is this node. By based on the color, we can classify all of them, saying that at this stage it is this, and next stage it is this. So we can probably do that using that. And and learning to contrast. So learning to contrast is basically used contrastive learning. So in contrastive learning, the main idea is to learn in a self-supervised fashion. So we do not have any specific set of nodes or nodes that we wanted to classify. We do not have the information of which belongs to which set of features. Then we use this contrastive learning principle. So what happens in contrastive learning principle is, when we are trying to design a classification network, so this contrastive learning mostly gets the good embedding representations that is required for our graph. Okay, suppose we say that I have a graph which has these set of connections. Suppose this is our graph, believing that 1 is connected to 2, 1 is connected to 3, and 3 is connected to 2, and this is the graph that we have. So what contrastive learning approach does is, so this graph is our original graph. So what it does is, it removes the information in randomly. It removes information randomly in each of the node. Suppose it removes 50% information in 1, 30% in 3, and 40% in 4. So 50, 30, 40% information, and it removes certain hyperedges. It removes the connection between 1 and 2, 2 and 4, 1 and 4, 2 and 4, and now it becomes a very new graph. So the information is lost, and certain set of hyperedges are lost. So it augments in this way. So this is called graph augmentation. So saying that we remove certain set of nodes and certain set of edges. That is the one transformation. The other transformation is randomly remove certain set of nodes and edges of certain features. Instead of removing 1, 3, and 4, it will remove 3, 2, and 4. So that is another set of augmentation of the same graph. Now what it does is, it gives to our neural network, hypergraph neural network. And when it's given to the hypergraph neural network, so it says to the hypergraph neural network that these two graphs are the same, and it will learn in that fashion. So when it learns that these two hypergraph pairs are the same, then the model or the hypergraph neural network tries to learn that, okay, these two hypergraphs, the hypergraphs are same, believing that whatever the information that we have given. So this is done at multiple times. Different iterations. It tries to do that. So I can give a small, a view, like example for that. I can simply use kind of a notebook, or so where shall I show to make it more little intuitive? Yeah. So probably I'll try to visualize them in the next week and bring it so that, this part is more clear. So it does two different augmentations. So this tau is augmentation strategy. It transforms the given graph of hypernodes and hyperedges into different space, and it encodes two hypergraphs. So what they call it, this has like hypergraph view pair. So this is a view 1 and view 2, and it gives to the network and tells the network that these are the two the same, and it learns in that fashion. So this is generally a contrastive based learning. So that's one way. And there are like other ways, like, they use MAE, so masked autoencoder. They mask certain set of hypernodes and hyperedges, and during the prediction, they try to predict that, okay, these are masked, try to predict the full. So these are like, certain set of missing features, try to predict the full. And that's how it learns to, acquire the representations. That's also one way. So here we see there is a contrastive loss. It tries to find out similarity between the first augmentation of, so here P, we call it as we have seen, P is like the hypernodes, the information in the hypernodes. And P double dash is P single, P prime or P dash is single view. And P double prime or P double dash is basically a second view. They try to find the similarity. In order to find similarity, we can use cosine or, Euclidean distance, or basically any type of distance that could actually work. And we use this loss function. This is called normalized temperature, cross entropy loss. This tau is basically the temperature coefficient that is used to train, tweak the model's performance. In the vision, it's mostly this loss was, adapted from like computer vision, where they use it for self-supervised visual representation learning. Similarly, we used in the graph where these are like two different graph views, and we try to minimize the similarity between those two. Also, we maximize the similarity between those two views, so that the representation what the model has acquired, it acquires like greater features and the aggregations what we are trying to understand. So this is one way, and this is at a hyper edge level. This is at a hyper node level. So the difference here we see is, instead of encoding the information in the hyper node, here we use hyper edge. So that's the only difference that we see. And at the membership level, what we try to do is, where we suppose the Q dash is an anchor, or we have another set of anchor, or basically the image that not image. So the graph that we actually used is basically called as an anchor, and from that we designed or derived two representations. One is first transformation and the other transformation. So first prime and second prime. So this anchor is basically this acts like an anchor and tries to maximize the representation between these two. So yeah, so these are the different types of laws that they have previously have used, and recently there are like more number of works. Not recently, 2020 and 2022. The most works are like predominantly in the line of the self-supervised fashion, because that is actually giving more performance than a supervised version of GCN. Suppose we take a simple GCN and a self-supervised GCN. So the self-supervised version is performing better in terms of understanding the features. And in most of the real world scenarios, we do not have like explicit labels. So this is one of the good way of trying to learn the representations. So, and learning to generate. So once I have mentioned that MAE version is basically trying to, you have a graph with missing set of features and missing set of hyperedges. And this hypergraph, we try to predict the missing set of nodes using a masked autoencoder, and it tries to predict the complete graph from the missing set of hypergraph. It tries to complete the complete hypergraph. So that is one of the type of generating ground truths higher order interactions. And we assign certain because we already know that these are the certain this is how the structure it has to be. And when we are trying to predict in the future, then it aligns with the ground truth that it actually has. So the hypergraph augmentation, the node and hypergraph subset encoding, the loss functions are detailed similar to that of that only. And yeah, it's more of the similar strategy that they encode. It's not a change that we see here. And because that these two parts, we need a little more in depth of understanding with cleaner visualizations, because it's more intuitive. This is more of theory oral explanation, but when I try to make sure that how these functions actually make difference using designing a graph or matrix and multiplying them and showing that how is the change, that makes more sense using a good visualizations. So probably I'll do in the next set of weeks when I have more time dedicated to this. So we have seen that we have the reductive structured. How do we design a certain type of structures? The reductive transformations or non-reductive. So the type of embeddings that we have, edge dependent or not, and we have certain set of aggregational principles. Are they learnable or not? So these are the set of works that people have. These people have curated for our interest. So we can see that we are mostly focusing on reductive transformations as this. So we want more of non-reductive transformations like star, line, and tensor, because we wanted to plot a hypergraph and plot the higher order interactions, learn them, and once we learned those set of interactions, we wanted to retrieve back the hypergraph and see where exactly it's reflecting. So the non-reductive transformations are more of useful for our case. And for the target selection and the message passing mechanisms, we want to learn the hyperedge features, and it should not be uniform, because it varies from one set of hyperedge to that of other. So it should be variant. It should not be uniform. So we use a learnable pooling mechanisms or whatever the mechanisms that we have described. So we want to focus only on the learnable parameters. So here we have seen the target selection and so the representation. How do we encode the messages? So we will encode only the messages that are dependent on the set of messages that we already acquired. So, and we have to apply a set of local and global attention too, because when we apply global attention, the whole hypergraphs get a certain set of feature dependencies. But whereas when we apply locally, we can say that local region is the motifs that we build across certain hyper edges. So we have an hyper edge across a small motif, believing that these has to have a certain set of attention. Then we have to use local attention in that space. And coming to the objective function, we can try out using a supervised mechanism, because already we have labels at each and every timestamp of the embryogenesis. And also we have or we can apply the self-supervised version, trying to understand these are the set of hypergraph interaction. Can we give me the best interaction based on the random set of the missing nodes and edges by reconstructing from the given graph? Does it will it be able to acquire like good representation? So we can try out like this different message passing mechanisms first, and we can next try out certain set of training principles. One is supervised way and one is contrastive way, because contrastive way is yet to proven good results in the previous standard citation networks and other. So I believe that the contrastive learning could be also useful. So we have, of my thought for the given data, I think non-reductive transformation is the right approach. Then we have to try out two or three different type of message passing mechanisms, and then after this we can try out learning that in a supervised or a unsupervised fashion. So this is what from the paper, and they have also given And these are the set of works which we are trying to understand. I said, when I said these, I mean, like when we are using only non-reductive transformations. So reductive, no, then we can focus only on this work. And later when we say that, edge dependent, then mostly are edge dependent. So, and then are there aggregation learnable? So we focus on like the learnable aggregations, and there is edge dependence, and there is no reduction. So we can just focus on certain neural networks that group into this and read about more what it's like, and go make a progress based on this. So any questions?
Really some interesting things you brought up. You talk about message passing. That's like a standard thing in graph neural networks. So if we're applying it to biology, what are the messages? So the messages are, well, they can be a lot of things actually. You can have like, different dependencies, which can be messages. And so in biology, we have actual messages sometimes. We have like signaling, but we also have things that get inherited. So those are also messages. Yes. So, there are a lot of opportunities to like kind of play with the message passing idea quite, extensively, and see how that, different types of messages, it would require different types of data sets, or maybe synthetic data sets, to see what, how those networks would be different, or what their learning capacity is. So if we had one network, for example, that was signaling based, and another that was inheritance based, and maybe a third where you transmitted forces, like this is where you have a mechanical network, and it's like things going from one place to another. Those are all message passing, but they result from different types of networks, different types of learning capacities, and things like that. Let's see. Yeah, and then there's this part. Let's see if I can find it here, where you did the different there were different views of the network. So this is something in machine learning that people have done a lot, with like different views of data, or different views. Yeah. So could you go into that a little bit more?
Should I explain, or if you give me a little time, I can sketch it out a little bit in more detail?
Yeah, that'd be good.
Oh, well, I just wondered what kind of math that was. Looks like linear algebra to me.
Yeah, a lot of it, yeah. A lot of it is linear algebra.
Okay. Because I think they're using this with the tensegrity models somewhat.
Yeah.
Some of it looks familiar.
Yeah, there's probably mathematical continuity between like a lot of machine learning and stuff like tensegrity models, or at least you can state it the same way. So that's interesting. Interesting connection.
They start off with crystallography to name the nodes because it's 3D.
Right.
And then they go into, well, it looks like some of this math with it. So I would like to be able to do this.
Yeah.
Just give me a second so that I'll.
Oh well, I'll turn this off. Sometimes it interferes.
So I'll share my screen once and I'll try to explain what can be seen like. I mean, suppose yeah. Suppose this is our hypergraph, and when we are trying to do type of a star graph type of expansion, saying that okay, these are set of the the hyperedges or the.
I don't think you're projecting the right thing.
Oh, sorry. Oh.
I can see your face, and then I can see your PowerPoint slides. That's it.
Oh.
There we go. I see it now.
Yeah. So I'll try to make it.
That's good.
So are we able to see the full screen?
Yes. Yes.
Okay. That's great. Suppose these are the type of graph that we wanted to build. I'm drawing just a rough graph so that for an intuition, it will look good. And just so this is just a star expansion, and we can take it like another expansion too. So it's just for the intuition I have drawn, so that it's just represented similar to that of the hypergraph that we build here. So here this node has interaction between the hyperedge green color and the blue color. So similarly, these are the hyperedges. So green and the red, sorry. And this yellow shares with the red and the yellow neighborhood. So I have wrongly interpreted that part. Probably I can remove that. Okay, so this is not it. This is it. Yes. So this has like two edge connections. So this is how our embedded this hypergraph into this the given hypergraph. Now what we are trying to do is, suppose we have doing a transformation T1, saying this has like a transformation. What we do, what I'm trying to do is, this carries an information of I, suppose I1, I2, I3, and here each and every node carries information. These hypernodes carry information of, suppose per se like G1, G2, G3. I say node, right? So it's better to use N1, N2, N3, N1, N2, and N3, and this carries set of informations. So when I do this transformation, whatever the information present in the green node may be reduced to a percentage of 20. So this is the information that is present in that N1, suppose, and these are the features that it has. What I'm trying to do is mask these set of features and keep it empty. so that it will try to, the whatever the information it has been reduced. Only a certain part of information is given, and we are trying to remove certain set of nodes. So then this transformation should look like, so here we have removed one connection to this, and this node is suppose empty, one node, suppose this is empty, and here we have 3 connections, and here I'm missing out one more node, so this is also empty, and this has a connection between this, so which I have removed. So the removed connections, I'm showcasing it like a dotted line, so it will be clear. And here I am trying to remove the connection. So this is how our new hypergraph looks like. So this is one transformation, and the information that was present here inside each and every node is again compressed or reduced by some proportionate randomly. So we have algorithms that do remove certain set of information. This is called transformation 1 or view 1. We say these are like different views. Next, we try to use another transformation T2, which has a different set of alignment. So this removes certain set of nodes and certain set of information, and it looks little different. So suppose this is our hypergraph. So instead of removing these two, it removes these two information, and this is connected. This was connected previously. This might not get connected. So this is dotted. So this is how the pair of interactions can be removed. I just gave an example for hypergraph. In graphs, this is like a standard scenario. So what now it does is, so we have transformation 1 and transformation 2. So in the next step, what it does is, we have transformation 1 and transformation 2. It gives to a graph neural network or hypergraph neural network, and it gives us saying the representation that this is R1 and this is R2. So whatever the loss function that I have explained, exponential of the representation 1 comma representation 2 divided by tau, this is the parameter, temperature parameter, by summation of the, suppose we are doing it by the nodes, so summation of exp of representation of, suppose this is I, Ri comma Ri of 1 2. So this does for all, and this is for like individual, and this is how it calculates the similarity between R1 and R2, saying that whatever the transformation that happened here and transformation that happened here will go through a GNN, and it will give 2 representations, and these 2 representations are same. So this is the loss function that says that these 2 representations are same. So what the network believes, we are trying to learn this hypergraph neural network, right? So what this network believes is, so whatever the view that I got here and got here are the same, and it learns in that fashion, and with the limited information that it has at each and every node and limited hyperedge interactions. What we do during the test time, so this is while training, during the test time, when we have less number of labeled information, we pass our new hypergraph, so say GH, and then we give to this hypergraph neural network. Then the set of embeddings it gives. Embeddings or the representations during the test phase, what it gives, this is more significant and valuable than the information that was carried out by training in a supervised fashion. So that is what the principle here works around. So this is how it generally works, and
you would use it in contrast to sort of labeled data. So if you didn't have labels,
if we didn't have the labels, we use that to contrast one with the other and learn the representations.
Okay.
So this is like more recent works that Morgan have attached so many works like recently published and all, right, in the group. So in that group, we see these are the most recurring papers that we see. So they tweak the loss function in certain fashion to improve the performance of certain set of networks. So this is barely applied in biology yet, I believe. So we have to exactly see where the application fits around and what kind of biological interactions it can form, how meaningful are they, and it will be more useful for us to understand in detail like what this will give us.
Yeah, that's good. That's good. So yeah, I've got like all the questions I had. I think you went through a nice sort of typology of some of these different methods. Like, how do you expand and do the sort of the details of message passing? And I guess the question then is like, how do you apply that to biology? And, there are different types of biological message passing, and how does that relate to what we might do in a graph neural network? And how do we, because a lot of times in like generic network theory, people use message passing for like determining causality. Like if one node affects another node, what is the, how do we know that from, like we basically would have like a connectivity matrix, and then we would have like a message passing matrix, which would be like, if something originates in one node and it ends up at time 0 it would be in this node, at time 1 it would be over in this node. How can we determine that flow? So you'll see that a lot in network neuroscience and some applications to like, hydrodynamics or something like that, where you have to from maybe a time series or from a separate data set where you have actual information about incidents, where, what is that? You have to reconstruct things moving from one node to another. And then that gives you causality because you know that activity in this node caused activity in this node, and it goes across the network. And you have to filter out the confounding signals because, of course, it's not linear. You have interactions going every which way. So.
Yeah. So I'll look into this interaction parts, how this can be exactly manipulated in the biological space, and the causality that you mentioned. I mean, like the how they interact. So the cause and relationship that we actually have, that is more important when we're trying to model. So I'll look into that. So.
Jayadratha had posted an arXiv paper in the chat. So this is for experimenting with different kinds of message passing schemes. There's a nice paper called PNA. That's a method, I guess. It shows that we can experiment with any permutation invariant aggregators. We can combine them. This is the paper, Principal Neighborhood Aggregation for Graph Nets. And graph neural networks have been shown to be effective models for different predictive tasks on graph structured data. Recent work on their expressive power has focused on isomorphism tasks and countable feature spaces. Then they extend this to include continuous features, which you see in a lot of real-world domains of data. So a lot of biological data, in other words, that we can't segment easily. Or, if we segment them, they're kind of artificial things like, when we segment cells or segment an embryo, say, into cell nuclei, are we capturing sort of individual cells, or are we capturing the syncytium that we've been talking about? Or, do those nuclei sort of form the basis for cells, but then those cells are in like a migratory flow? And do we want to actually capture the flow instead of the individual nuclei and, all those sorts of things? So we can do that sort of thing. Here they propose principal neighborhood aggregation, or PNA, a novel architecture combining multiple aggregators with degree scalars. Finally, we compare the capacity of different models to capture and exploit the graph structure via a novel benchmark containing multiple tasks taken from classical graph theory alongside existing benchmarks from real-world domains. With this work, we hope to steer some of the graph neural network research towards new aggregation methods, which we believe are essential in the search for powerful and robust models. So those aggregation methods are also interesting. What did you have any words about that? Like what is the? So I guess what we're trying to do with aggregation is we're trying to figure out what are the constituents of a hyper. Correct?
Yes, sir. Actually, this work which Jayadratha has shared is focusing on the graph neural networks. So it's more relevant when it comes to the shared representations that a graph neural networks carry out. It exactly does not fit into the hypergraph, but it can be definitely tweaked into the formulation that we have. And yes, sir, we have to look more into details about it.
Well, I mean, I'm just thinking about like how if we're talking about hypergraphs, how that process works, or you're trying to aggregate things into hypernodes.
Right.
You might also do this with categories of cells or cell type. I'm thinking more about the biological connection. So you're really trying to just find categories, find mean behaviors, if that makes sense. Like you're trying to find things that can be aggregated together. It's always a problem that we have in classification, like what things go together, what things don't.
Yeah.
Right. Yeah, that sounds good. That's all very good stuff. Thank you for that presentation. And if we're kind of walking through, Lalith gave a presentation last week on this paper, so we're kind of walking through it and trying to unpack it and trying to get a sense of what's possible, how it connects to biology, and so forth.
So, and also adding to that, we still need more to understand exactly how does it fit to the biology. So I was just giving a fair and thorough thorough understanding of how this hypergraph neural network works and how it can be used, but how it fits is like a stronger research question, and it needs more time.
Yeah. Okay. All right. Well, that's it for today. I think Hussain was joining us, but I think he got knocked out of the room. I didn't know if he had something to add, but anyways, I guess that's it for today. So thank you for attending.
Okay. Thank you all.
Have a good week. Okay. Bye.
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 Thanks. Bye.
Thanks.